All right. Hello, everybody. How you doing? Doing all right? Almost Thanksgiving. Yeah, one more week, right? Okay. I don't quite have the exams finished grading. I expect to have them ready for you Thursday. So I probably will be going through exam solutions then. That leaves us with discussions on biological oxygen demand today and then on Tuesday next week. This is kind of what happens after we treat the wastewater, right? So we discharge the wastewater, or maybe we accidentally discharge untreated wastewater. What's going to happen? So it's kind of adding some of the context to our wastewater treatment a little bit retrospectively. And I think we'll have a little bit of time after the break to get into a little bit of what else can we do with our waste stream, what about the solids in the waste, all that sludge that we accumulate and collect, what do we do with it exactly, how can we extract some nutrients, that kind of stuff. And of course, some review for the final exam. So that's about where we are. I think last time we kind of wrapped up the activated sludge stuff. If I haven't posted the solutions to that problem we were working, I will do so. Feel free to remind me if it's not up there. I think it might be up there already, or I just need to put it back up there. But I plan to get that up for you in case you wanted that as some extra practice. Okay, so the oxygen demand stuff, this will tie back to some of our mass balances. And this is going to be mostly like a look at some rates in the environment, partly physical with oxygen exchange with water, and partly biological with how fast microbes are eating stuff. But the extent of biology that we've covered so far is basically it, right? We learned something about the growth equations, and it turns out that at that level, we're just doing math, not biology, in some sense. We need to know a little bit about the biology to understand it, but in general, it's not a crazy thing going on. A little bit about the theory, some stuff we already talked about, and then we're going to start talking about practically how do we measure this stuff, this oxygen demanding substance. Well, it's pretty simple, so it'll feel pretty basic this time, and then we'll get into a little more of the math and the modeling next time. So, BOD, biological or biochemical oxygen demand. Like we talked about briefly, this is essentially the food. We might call it biodegradable stuff or biological oxygen demand, biochemical, whatever the case, whatever way we want to call it. Microbes, biological entities can use it, and in doing so, they're going to breathe, just like we do. We breathe in and we breathe out. That's oxygen coming in and CO2 going out. What's happening there is the carbon is changing from what we might call a reduced form to an oxidized form upon reaction with the oxygen. That releases energy, which the cells are using, which we are using as our energy source, right? So if we starve ourselves from carbon-based foods and don't ever eat anything that has some carbon bonds like that, well, we're going to eventually starve and have no energy, right? That's the thing. So this is the amount of oxygen then. It's kind of like taking a breath test in some sense to say how much CO2 is coming out versus oxygen going in. That's what we're going to measure for the bacteria. And in doing so, we will get some estimation for how much food they're eating and how strong of food this substance has to be in terms of how much oxygen will be required by biology. So the overall chemical equation, we could call it, is oxygen plus these dissolved organics that we're talking about is going to yield CO2, the breathing out, and new cells. So some of the carbon, they'll just take and build new cells and replicate and all that. Some of it's just going to be sent back out as CO2. And in the process, we are consuming oxygen. Okay, that's BOD. And we're going to talk mostly about BOD, but I want to take a side note to say there's also some theoretical maximum oxygen we could demand if we did all the chemistry all perfect and say this chemical reaction with glucose, as an example, could take exactly this many oxygens to do it. And at the start of this semester, we did a few simple chemistry experiments or reactions to say, oh, well, how much oxygen does it take to combust butane or something? And that would be a theoretical amount. So for example, for glucose, we might say there are 6 carbons here. So we might take some number of oxygens and we'll create, let's say 6 CO2 and some number of waters. And we could balance that equation and find exactly how many oxygens and how much water we're getting from this reaction. But that's just in theory, right? In practice, maybe a portion of these are then built into a cell instead of oxidized sort of like a combustion reaction. Instead of oxidizing it, maybe some of these become cells. Maybe there are some organic compounds that are just not very digestible, right? So in practice, the theoretical oxygen demand will generally be higher than the actual. So this theoretical oxygen demand will definitely be higher than BOD. Because in theory, we could get all of it oxidized. In practice, not all of it's going to. Now, there's one other way we can measure oxygen demand. This is somewhere between the theory and the BOD, as we see right here. So chemical oxygen demand is pretty convenient compared to both theoretical and biological because it's quicker. Theoretical, honestly, we're never really able to theorize that unless we have exactly a pure solution of glucose or something. We know exactly how much is there, we can calculate that. But in practice, in a river, in anything meaningful, there's going to be some random mixture of all sorts of things we don't even know what's in there, let alone how much exactly of each one there is. So there's no way we can do the precise stoichiometry on some random lake water. So theoretical is not very practical and would take a long time to calculate if we did. Biological takes about 5 days. So when we give microbes time to eat, we give them 5 days to eat. At a convention, that means we don't know our BOD until 5 days later, which is not super helpful if we wanted to know today. So that leaves us with chemical oxygen demand, where we are just going to blast our solution with some harsh oxidizers, give it all of this condition to burn, to oxidize, and measure how much oxygen was consumed during that process. So this one is pretty convenient in the case that it happens in maybe hours. So samples might be minutes to hours range for a COD measurement. Usually this will be high temperature, some oxidizer like perchlorates or something. Sometimes we'll add in UV just to spice things up even a little further, really make it kind of an advanced oxidation process. And whatever chemical can be combusted or can oxidize with those conditions, then will be. So some chemicals will be difficult and just simply won't combust, but usually we will get more oxidation than the bacteria could achieve. So that's why we're going to list COD, chemical oxygen demand, as higher. So this is just a quick overview of the ways we can measure the oxygen demand. Ultimately, if we do COD, we're pretty much getting everything to CO2, water, and then other products like nitrogen gas, N2. It's usually we consider this complete oxidation, or at least very nearly. Sometimes you'll see it written as complete mineralization because it's sort of a mineral instead of an organic form. Whereas the BOD, we're going to get some stable byproducts, but they're not all completely oxidized. So for example, nitrite and nitrate here could be taken, if we went further, to all the way to N2 gas. And some bacteria can do that, but we have to give them the right conditions. But generally, we'll find ammonia, nitrate, nitrite Ammonia, not so much if we give it plenty of oxygen. That's another source of oxygen demand. If we look at ammonia, we'll say NH4 plus, will take oxygen, some amount of it, I'm just going to say some, O2, to yield these guys. So even the ammonia, which is not a carbon thing, it's a nitrogen thing, can demand oxygen from these processes. Phosphate also, what you'll notice is all of these have oxygens attached, but in like biological material, they don't have the oxygens attached. And so we're going from non-oxidized to oxidized, and we end up with these partially oxidized or mostly oxidized stable byproducts. So that's just pretty common. And so you'll find a lot of these guys in wastewater, nitrate, nitrite, phosphate, and things like that. So that's another reason BOD is going to be a little less than the chemical. Okay, so that's just a quick bit of background. How can we estimate this oxygen deprivation problem, and what are our tools? So chemical oxygen demand, it's pretty good in a pinch. It's pretty good for certain circumstances. It's just not a direct correlation, or like not an exact port to how much bacteria will consume. Okay, so I kind of hinted at this a moment ago. There's a couple subsets of the BOD that we could look at. One is the carbon-based and one is the nitrogen-based. So the carbon is pretty straightforward. It's like a sugar or something. We have carbon throughout our cells. Most of what we are and the food that we eat is carbon, if we were to look at it. And it's going to be in this reduced form where we have, if we want to be all chemistry about it, fancy with chemistry, we're going to have some compound, probably some hydrogens as well in a lot of places, that's connected to that carbon, and usually not too many oxygens. Then we're going to oxidize it, and we'll just get that R, whatever was there, plus our CO2. So we're adding oxygen, getting CO2 out, consuming the oxygen for that. Another one is this ammonia. So NH3 plus oxygens will yield us, if we balance it, this is not balanced, can yield us nitrates and nitrites. So we could talk about the nitrogen cycle, and I'll just quickly go over it. There's a lot of nitrogen gas in the atmosphere. It's most of what we breathe. It's about 78% of the air we're breathing right now is N2 gas. So there's a ton of it. And usually it's a biological process that takes it from this gas that doesn't really do much into some biological component. So if carbon is a major component of life, nitrogen is the next big component, typically. And we even talked about that ratio of carbon, nitrogen, phosphorus a couple lectures ago. So it's important. Usually it's a biological activity that takes N2 gas to some living matter. That would be called nitrogen fixation. We could also get some fixed nitrogen by lightning. So every lightning strike tends to convert a lot of N2 gas into nitrites and nitrous oxides in the atmosphere. And we have the Haber-Bosch process, which can do it. It's energy intensive, but we convert some N2 into fertilizer, which is huge because that allows us to improve the amount of nitrogen for the plants that we want to grow to eat. Okay, so we could look at the details here, but basically we have a circulation where, based on where you are in this system, it will be maybe nitrogen gas, maybe it's now some sort of organic nitrogen, and then it's released as a sort of a reduced form, NH3, NH4 plus, and then back to some sort of oxidized sort of form, and then all the way back to N2. So it cycles. It's a natural cycle. As we do farming and things and we fix nitrogen ourselves, we create an imbalance in the environment, and so sometimes we have to concern ourselves about that. Wastewater is one of those moments where we say, okay, can we control how much nitrogen we're discharging so that we avoid overgrowth of bacteria and things in the environment? The oxygen demanding component of that can be important, but also just even nitrate that's not an oxidizing issue could be a separate issue of accidentally promoting too much growth. So all of that is a kind of on our minds as we regulate nitrogen in our wastewater. All of this was to say that ammonia itself can be an oxygen-demanding substance. And it can be bacteria or other biological matter that will take it and do this process. Okay, so back to the kind of generic BOD. There's a few assumptions, a few principles we need to know about and think about as we consider how to measure BOD. You'll see I put a little subscript 5, so BOD 5 is our very typical convention. There's not actually a real reason we can't do BOD 3 or 4 or 7 or something, but 5 is a nice, number. It's, 5 work days in a week. It gives bacteria a reasonable amount of time to grow, proliferate to the point where they can do the consumption that they need to do before stopping the experiment. So it's just convention, really, but it would not make sense to do half a day. It's not enough bacteria, not enough time for them to do anything. And at some point, they kind of stop consuming much, so it doesn't make sense to do too much more than that. So 5 is a good number. What we do is we take an airtight bottle. They often look like one of these little culture jars I have here. These are kind of a better example. We block it from any light that could cause photosynthesis, because if we've got some algae in there or something, then suddenly we're converting CO2 back to oxygen, which is exactly not what we want to measure. We're just wanting to measure how much oxygen is demanded. So we'll put them in dark. If we had a clear bottle like this, we'd definitely put some foil over it and cover it real nicely. Maybe we just take these amber vials, seal them nicely, and typically, as we see on the left here, we will also seal them with an oxygen probe in there. So we can monitor how much oxygen is in there over time. So once we have that condition, then we allow natural biological activities to go for about 5 days. We would make sure that this is not like freezing cold in a very cold lab. We might even incubate them at a certain temperature to make sure that they're plenty active. We need to make sure that there's enough bacteria in there to do the growth. And if we're dealing with something like wastewater, there's a good chance there is. However, we also need to dilute them very often if we're doing something that has a lot of BOD, because water doesn't contain a lot of oxygen. And so if we fill up a bottle with just water that has something like 8 milligrams per liter of oxygen, then we can't measure any more than 7 or 8 milligrams per liter of BOD. That's just our limit. So we need to dilute our waste into the water so that we can have a measurable range. So there's like some small details here that we need to take care of in order to do the measurement properly. Now, if we dilute it too much, then maybe we don't have many bacteria anymore, so we have to add some bacteria. So all of that is kind of covered in how we do one of these tests. And that's going to be what we work towards here so that we can formally get this BOD test. So we measure oxygen before and after our system, and ultimately we could describe the very simplest form of our math here would be the BOD 5 for our whatever we're doing. And by the way, we were calling this S for substrate, right, in the previous couple lectures. So we could say that the BOD 5 is going to be equal to, on a very simplistic view, this will be the dissolved oxygen initial minus the dissolved oxygen final. This will get a little more complicated when we need to dilute and do other things, but this is the basics, right? It's before minus the after. Stupidly simple, right? I'm just going to note so we'll get it a little more complicated, but at the very baseline level, this is what it is. Just before and after measurement in a little bottle that's sitting in the lab. Okay, so the first complication is dilution. And so we're going to take that little equation I sketched and make it a little more formal by adding a dilution factor, by dividing by a dilution factor when we're done with it. So basically, if we took a bottle and filled it 10% with the wastewater and 90% with dilution water, we ultimately have to multiply it by 10 afterwards to account for that dilution that we did to know the real concentration of the oxygen-demanding substance in our sample. So that hopefully is intuitive or should make sense. And so this dilution factor then is going to be what percent or what fraction really of the bottle is the waste. So P is our dilution factor. So if we have a container looks something like this, we fill it to the top, and we have some volume of dilution and some volume for the wastewater, then that's going to be our system where P is the volume of the wastewater divided by the total volume. So this is V wastewater, or it could be like a river or lake sample. It doesn't have to be wastewater, but usually it would be, divided by V total. Doesn't really matter which way you look at it. We're not typically going to add anything else aside from a dilution and a waste. We might add some bacteria seed as well, but that'll usually be incorporated into the dilution volume. So hopefully that kind of makes sense, right? If we divide by this dilution factor, that's effectively like multiplying by the inverse of the dilution factor, meaning, okay, we diluted it by 10 times, we're going to multiply it by 10 to get our final answer, right? Okay, so these are all just described here nicely. DOI for initial dissolved oxygen. So DO is dissolved oxygen. DOF, that's our final dissolved oxygen. And we're going to do oxygen in milligrams per liter, pretty much always. It's pretty convenient. The saturation at room temperature for water is typically around 8 to 10 milligrams per liter. If you go a little colder, it goes up a little bit. So if you have like a really cold stream, it's fresh water, maybe you get up to 15, 16 milligrams per liter. You don't really get up much more than that. And we're not going to do a BOD test in a cold condition because then the bacteria are refrigerated and not going to grow very quickly. So we'll do pretty much room temperature, maybe slightly incubated. So we have enough oxygen and enough heat for the bacteria to do their thing. Okay, so this is enough to start solving problems. So let's give it a run. This is a pretty simple one. We have a 10 milliliter sample of sewage mixed with enough water to fill a 300 milliliter bottle. That's quite typical, by the way, so we'll use a lot of them. Probably all of our examples will be 300 milliliters. Has an initial dissolved oxygen of 9 milligrams per liter. Then it says to help assure an accurate test, we want to have some buffer. The little probes are not super accurate necessarily, so we want to make sure that there's at least a 2 milligram per liter drop so that we're confident that it dropped. That kind of gives us a little more confidence here during the 5-day run. And the final should be at least 2 milligrams per liter remaining. So again, because these probes are not super sensitive, we're trying to make sure they're in a good range for this example. So the question then is, for what range of BOD5 should this dilution, or would this dilution produce the desired results? So we need a range of BOD5. So we should be able to find a max and a min. And recall we said the equation, it's what we started with minus what we ended with divided by that dilution factor. All right, so give that a minute. See if you can piece that together. All right, did you guys get some answers? All right, so the drop that we're referring to here, that should be simply the in the bottle, the initial minus the final, right? So that's what we actually observe. So when the text is talking about there should be this much drop, that's not accounting for the dilution because that's just what we're observing in the bottle itself. So we have like 10% wastewater, the rest dilution water. Of course, they're mixed together, obviously. But we can define that the P then as 10 milliliters over the 300 total. So to fill a 300 milliliter bottle. So that means the dilution factor is 1 over 30. Of course, we can get a number for that, but I think it'll be more convenient not to this time. So then the max amount is basically the max drop that we are allowed. So if we start with 9 and we need at least 2 left, then the max drop we can have is 7. So 9 minus 7 divided by the 1 over 30. So the 7 is coming from the fact that we still need 2 remaining. So this will end up equaling the 2 remaining divided by 130. The minimum should be 9 minus 2 because it was a minimum drop of 2. So this should be 7 over 1/30. Now I think I said that backwards, right? Because I said that backwards because 9 minus 7, yes, that is a drop of 2, but that's only 2 was demanded. Right, so that's actually the minimum BOD case, because this will give us a smaller number. That would have been clear as soon as I did the math for us. But what I should have said, and this is where just the wording gets, we have to be a little careful. I'm going to calculate the minimum and say that the minimum BOD has the smallest drop in dissolved oxygen. And the smallest drop we're allowed to have is 2, which is 9 minus 7. That's the better way to say it. The largest drop corresponds to our maximum BOD for this condition, this range. That's going to be a drop of 7 because we need 2 remaining. So the drop here for the max is 7. And for these, we can take 30 and multiply it by that number. So 30 times 2 is 60 milligrams BOD per liter. And down here, 7 times 30 should be 210 milligrams BOD per liter. Of course, maybe I should say BOD 5. Okay, does it make sense? So pretty straightforward there. Next up, when we dilute and we have to add bacteria, like I mentioned, well, it turns out this is going to be just a very small headache, because when we're adding bacteria, we have to make sure that the bacteria themselves are kind of happy with whatever state they were in beforehand. And it turns out it's very inconvenient to filter out all those bacteria into a nice, clean, pure solution before adding them to the dilution water, because they have to have something to keep them growing or satisfied, at least. So it turns out we're going to add a little BOD as we're seeding the water. So it's unavoidable, but we have to add just a little bit of BOD. That means our math just gets a tiny bit complicated, meaning, you know, when we calculate our BOD, we have to separate what was in the wastewater versus what was in the seed water that we just contaminated our sample with. So it's a small inconvenience. It's a tiny bit of algebra. So the point is, we have an equation that we can derive here, and it's a very simple mass balance, and we'll have an equation that you can use, right? So the deal is, we can take a look at the BOD5 for the mixture times the volume of the mixture, and that's going to be equal to the total BOD in the 2 volumes that we're adding to our bottle. Okay, that's our mass balance here. It's very simple. We have, again, some volume of dilution water that has now a BOD for that dilution, and a volume of, that was probably the wrong way to write that. Usually the wastewater is a smaller amount. So we can look at the BOD for the wastewater, and the volume for the wastewater, and the volume for this dilution water, which also now has a BOD for that dilution water. Now, this is only if we are seeding it. Sometimes we don't need to seed it. So if you have a problem that says the bacteria is seeded and blah, 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 essentially what we're going to do to know how much BOD is in the seed water is do an experiment, 2 experiments, one with the mixture and one with just the seed water, just 300 milliliters of the seed water. So we'll end up with 2 bottles, and we'll get a result for one, which is very simple. Use the math that we did at the very beginning with not even a dilution factor. And then we'll have the second one that has this mixture that we can then calculate, okay, how much BOD is coming from the wastewater versus other stuff. So the mass balance here, coming back to that, BOD in the mixture times volume of the mixture, this should typically be 300 milliliters, times the BOD, or is equal to the BOD of the wastewater times whatever volume we use there, plus the BOD in the dilution water times whatever volume we use there. Now, it'll be kind of convenient to convert this to P, the dilution factor, and that volume. So then we can get kind of everything in terms of the dilution factor. So we can do a little bit of algebra from this, the P dilution factor here, and we can say 1 minus that is going to be the volume of dilution divided by the volume of the mixture. It just takes a little algebra to get there. Don't worry too much about it unless you feel like it. Down here on the denominator here, that would be volume of the mixture. Okay, so with that, with this generic mass balance, what we want to do is find BOD of the wastewater. So we'll rearrange this equation and probably convert the volume of the wastewater, volume of the dilution water, into the P factor, so that we can get an equation. So that's what we're doing here. We start with this mass balance. We're going to solve for BOD wastewater. When we do that, we will get a form that looks like this. We separate it. We subtract BOD for the dilution from both sides, divide everything by the volume of the wastewater. We end up getting BOD of the mixture times VM divided by VW minus BOD for the dilution water times V dilution divided by VW. We can then rearrange a bit, do a little bit of algebra, and get this equation, which you'll have on your formula sheet. BOD of the wastewater is equal to BOD of the mixture minus BOD of the dilution water times 1 minus P. So 1 minus the dilution factor. So basically that's saying the portion of water that is the dilution stuff, instead of doing the portion of water that is the wastewater. All of that divided by the dilution factor. So it is pretty intuitive once you look at it. The direct derivation is intuitive enough. There's a bit of algebra with the fractions and stuff, but it's nothing super fancy. So that's our equation, and that's how we're going to address the situation when we have a seeded dilution water. And we need to seed it so that there's enough bacteria to do the job. Okay, I mentioned this already, but we need 2 experiments whenever we're doing the seed thing. So we're going to have one that is completely filled with seeded dilution water. The next one will have some wastewater, however much we need, and then so this one will, in total, will be the total mixture. And when we do the DO initial minus DO final for both of these scenarios, we can get our results. So in this case, this is how we find the BOD in the dilution water, and we will describe this if we want to use this equation up here. We will describe this as B initial minus B final, where BI is the dissolved oxygen initial for the dilution. So it's another equation that you're welcome to use, but you don't really have to use. So if the B's are confusing, then all you need to do is skip back to this equation and say, I'm just going to find the BOD for the dilution. I'm just going to find it and figure out what that means and go from there. Because what you'll notice is this is exactly the same equation. We just are perhaps confusing it a tiny bit, if you want to look at it that way, by defining a separate term for the dissolved oxygen in the dilution vial. And so BF would be the DO final in the dilution bottle. So since the dilution bottle is not, nothing weird happens to this, there's no dilution for the dilution bottle, it is the result, the BOD for the dilution stuff is just the initial minus final. That's all it is, and that just goes straight back into the equation where we said BOD for the waste is equal to, right here, BOD of the mixture, which is what this portion is getting, the DO. So my point here is just to just to let you know where these pieces are coming from, right? So the BOD of the mixture is from this bottle. That's the DOI minus DO final. The BOD for the dilution bottle is the BI minus BF. Then to calculate the BOD for the wastewater that is in the mixture, we have to account for the 1 minus P, all that divided by P. Okay, we have 3 different BODs to analyze here. One is bottle number 1, one is bottle number 2, and the other is, okay, now that we know that, we solve for the one remaining unknown, and that's the BOD of the wastewater, or the sample. Does that make sense? Okay. So, hopefully, this is not a super confusing or difficult topic, but we just need to know the nomenclature, how it works, so that we can do the problems. Okay, so given that, let's put it to practice. Here we have a test bottle containing just seeded dilution water, has its DO level dropped by 1 milligram per liter in a 5-day test. Separately, a 300 milliliter bottle is filled with 15 milliliters of wastewater and the rest seeded dilution water. That would be a 1:20 ratio, so P is 1 over 20. That one experiences a drop of 7.2 milligrams per liter in the same period. What would be the 5-day BOD for the waste? So I'll give you a couple minutes on that one. All right, so probably had enough time to maybe get a little confused if you were going to, because we don't have any initial concentrations, right? Or even final concentrations given. So we don't actually need those values if we have a drop provided, right? So if we're told we have a 2 milligram per liter drop, then initial minus the final is 2, right? So what we can do instead is say, well, the DO initial in the mixture test minus the final in the mixture, that drop was 7.2. So we can go ahead and put a 7.2 here because it dropped by that much. Then we can do the same thing for the dilution water that dropped by 1 milligram per liter. And then it's a matter of putting in our numbers, right? So 1 over 20 is 0.05, it's like 5%, right? 5% chance to roll a 1 on a D20. So 1 minus that would be 0.95. So you get 7.2 minus 1 times 0.95 is 0.95. All that multiplied by 20. So this would be, well, we'll just pull out a calculator. Can't do all of that. Anybody have that answer? 125. Thank you. Yeah, and that looks like it should be correct, right? So we're going to take something here that's about 6 and multiply it, maybe a little less than 6 or thereabouts, a little more than. Multiply that by 20. That should be 125, or right in that range. All right. Does that make sense? Any issues on that? Okay. Okay, so we've got a little time left, so I'm going to go ahead and start on kind of the modeling section. We're going to end up arriving at some complicated equations that we can use. They're pretty neat, and we're not going to get all the way there today, so we'll come kind of back to this. But at least I want to start by describing the principles of how we might model the oxygen concentration in a stream or a river. So when we discharge wastewater, it's going into the river, river's flowing, there's going to be biological activity happening. There's also going to be the physical re-aeration of that water. So in our BOD test, we fill it all the way and we seal it off so there's no re-aeration. So then we're just measuring what's in there. In a real system, we do have these physical processes, and so we need to balance, we need to find mass balances for the oxygen content as well as the amount of BOD, the food content there. So that's kind of what we're going to head towards. It's actually going to be in a way similar to like a biological reactor, except more catered to a natural system. And we're really only going to deal with a river or a stream because that lets us deal with a plug flow condition and track how far or how much time has gone by before we reach a critical point where the dissolved oxygen reaches a minimum value. That's often what we really care about because, you know, if the stream is going for miles and miles, well, at some point, that waste that we discharged causes that stream to reach a minimum oxygen content. That's where the fish and wildlife would be most vulnerable. And so that's kind of a target in our mind is when does that happen and how bad is it when it happens? So we'll have some fancy equations to help us with that, but we'll develop the pieces along the way, which I think would be a pretty interesting connection to the rest of the stuff we've been talking about. Okay, so we have deoxygenation. That's this BOD action, right? Microbes degrading BOD means we are consuming oxygen, as we just discussed. So we have some rate we might describe that encapsulates that process, how fast it's happening, a KD for deoxygenation rate. This is a per time unit. That's going to depend on how much BOD is there. Okay, so first order, I'll say first order with respect to the BOD. Next, we'll have a rate of deoxygenation that we can calculate using that KD. So if that's the rate constant, then we can have the rate at which it's going to be demanded. And we can define this as KD, so rate is going to be equal to KD times the initial amount of stuff that remains, amount of waste, this L naught. We'll talk more about that, but that's going to be the ultimate BOD, if the ultimate amount that could be consumed, that happens to be there initially, once we discharge the wastewater, times e to the minus kdt. Okay, so this rate equation is a little funny. It's a little different than what we've dealt with before, but we're just going to, it kind of looks similar, right, with the exponent, but it also has that kd out front. We're going to set that aside for the moment and just say that's the rate equation, and we'll build from there. Okay, so we'll come back to plug that in to the wider picture later. Now, in terms of the physical process, the re-aeration, how much are we shaking that water and exchanging it with the atmosphere is kind of what matters here. This is going to be proportional to how much oxygen is missing and how much oxygen that could be there. Well, I guess that's kind of obvious with the missing component, right? If we have a very cold stream that can take a lot of oxygen and it's deprived of oxygen, then there's a big gap. That means that there's going to be a big gradient driving oxygen into the water. So the bigger the deficit, the stronger the faster this rate will happen, the rate of re-aeration. There's also going to be those mixing factors. So the re-aeration rate then depends on that deficit. And here, I apologize, this could get confusing. We're just going to use capital D, I'm following our book's terminologies here, for deficit. That's different than dissolved oxygen. In fact, it's kind of the reverse. It's the amount of dissolved oxygen missing compared to dissolved oxygen at saturation. So DOS here would be the saturation condition. So oxygen saturation, we might say as DOS. Versus the current, which would just be DO, or DO at some time, T. So here's where we're getting this deficit term as DOS minus DOT. So saturation minus what we have, we might have a 4 milligram per liter deficit. That's how much is missing. That's going to be the driving force for oxygen to re-enter the water. Okay, that'll be the thing that sort of drives, because the system will try to reach equilibrium between the atmosphere and the water. So Kr then, the re-aeration rate constant, another first order rate constant here, as we see from the units. This is going to be first order with respect to how much oxygen is missing, essentially. The rate of re-aeration. And we see that because we have the deficit to the 1 power, right? So if our rate equation is Kr times D, it's first order, depends on how much oxygen is missing, and we've got this rate constant Kr. And what is Kr? Well, this is the thing that takes into account how fast the water is moving, how turbulent it is, how much mixing do you get throughout the water. It's very very practical, empirical, not very theoretical. I mean, the theory is that the more it mixes and the more it splashes, the more contact you have, the higher that constant. But in practice, how do we get it? Well, we just measure it for a bunch of rivers and measure their width and their depth and their gradient or speed, and there we go. So it's sort of empirically derived. Kr is simply 3.9 times u to the 1/2 divided by h to the 3/2, where u is the speed in meters per second and h is the height of the river at its steepest point, m. So it's just some some parameter we can get, okay? And it's an estimate. I'm sure there are other ways to estimate it out there, but this one we can use, and it does a pretty good job estimating the rate constant for reaeration. So this is going to be high for a waterfall. It's going to be a rather large rate constant for a waterfall compared to a slow-moving bayou that's really deep, let's say, is going to be a very small number, right? Because it's going to depend on those different interactions. Okay, I guess that's probably good for today. Well, next class, I hope to go through the exam solutions with you, and then next time, with a typical lecture, we'll get back to this and kind of put these rates together to make a model for what's the oxygen concentration in some river downstream. All right, see you guys on Thursday.